Okay, so this is the video explaining experiments 4, 5, and 6. Hopefully you'll be watching this before you begin experiment 4. I need you guys to get out your lab procedures and turn to the experiment 4 standardization of sodium hydroxide page, which is page 6. So the point of experiment 4 is to make and standardize some sodium hydroxide. So if you look at the page of your experiment, it says to clean out a 0.5 liter bottle. You don't really need to clean the bottle. Those have already been cleaned, and the only thing they've ever had in it is that sodium hydroxide. So all you need to do is weigh out about 2 grams of sodium hydroxide. And when I say about, I mean about. It doesn't need to be exactly 2 grams. And put it into the bottle, directly into the plastic bottle that you have at your home base, and fill it up with water. You can fill it up all the way. You can fill it up close to the rim. Because we're standardizing it, it doesn't matter. Close the top, shake it, and get all that sodium hydroxide to dissolve. Sodium hydroxide is super hygroscopic, so I need you to be sure anytime you use it, you immediately put the cap back on. Make note, immediately recap. Super important because it quickly gets water in it, and then you don't get as much per gram as you should be of pure sodium hydroxide. Once you make your stock solution, that's what we're going to call it, your sodium hydroxide stock solution, you're going to obtain a sample of what we call KHP. That's short for potassium hydrogen phthalate. The formula for that is found on page 6 in the procedure. Use that formula to find the molecular mass. It is not the mass of potassium, hydrogen, and phosphorus. That would be wrong. You want to find the mass of the correct formula when you're doing your calculations. So you're going to weigh out a specific amount of KHP, dissolve it in some water, put in a few drops of phenolphthalein, and titrate to the pink endpoint. This is the easiest titration you will have ever done. And you did this earlier, and you did this in pre-AP actually. But this should be super quick, and I believe you can get 3 of these done in one session. So titrate to the normal phenolphthalein pink endpoint, and your mils are going to really vary based on how many grams and how much water you put in that stock. So I wouldn't put too much stock into these values. I would just take that first titration a little slow, and then you can bust a move through the second and the third titration. Once you're done with that, you need to calculate the average molarity of your stock solution, just like you did with your potassium permanganate. Once you know your average molarity, you can then find 2 standard deviations and throw out the data points that don't fall within that 95% confidence. But I promise you most of you will not have to throw out any data. So moving on from experiment 4 to 5. 5 is a super important experiment. In this one, you're going to be using what we call ion exchange chromatography to determine the percents of 2 other parts of our crystal. So in our crystal, we have some potassium ions, some iron ions. You know we have oxalate as well, and we know there's a hydrated part of the crystal which has water. So what we're concerned with in this experiment is our potassium and our iron. So the way the ion exchange chromatography works is you're going to have a syringe, and you'll see pictures of it in the PowerPoint here in a second. And the syringe is filled with a resin. We're going to call this our column. We're doing column chromatography. And this resin is made up of all these little polymer balls. And the polymer balls kind of feel like sand. It's kind of gritty. And each ball is saturated with a bunch of H pluses. The H pluses are surrounding every single one of those little balls. So what you're going to do is you're going to take your green crystal and you're going to dissolve it in a certain amount of water. And again, you're going to know a specific amount of grams of that. And you're going to pour that green crystal into the column. And you're going to run the green crystal through the column. So if we look at all the parts of the crystal, the first thing we look at is the definition of ion exchange. This is specifically a group 1 ion exchange. So for every 1 K plus that goes in here, 1 H plus comes out. So that's the first thing that happens. The K will literally change spots with an H plus on the ball, on the piece of resin, and then shoot an H plus out. The next thing that happens is with the Fe+3. The Fe+3, because it's so big and so positively charged, does not like the positively charged balls, so it's going to get shot out because it pretty much hates being in the column. So at this point, when you run through, we're going to have H plus and Fe+3 in the beaker below. The oxalate is negatively charged, so as you would imagine, the negatively charged ion is going to stick to the resin and stay there, and it will remain there. So the only thing that you do when you separate this chromatography, the only thing that's being separated is your H plus and your Fe+3. You will then take your beaker that has these two things and you'll do a titration. So let's talk about that titration. Here you have a column. I thought I had a picture of the titration in this. Where did it go? So I'll draw a picture of it. So backing up a little bit before we talk about the procedure, you're going to have in your Erlenmeyer, it's actually going to have to be a beaker, not an Erlenmeyer. You're going to have iron, and you're going to have H plus in this beaker. And you're going to be titrating it with the sodium hydroxide that you standardized in experiment 4. As you do this, it's going to create a double equivalence point. The first equivalence point represents the amount of H plus. The next equivalence point represents the amount of OH minus. So the H plus is really your potassium, right? So at the equivalence point, you know the moles of NaOH because you'll know the mils of NaOH, so you can use your molarity times mils to get moles. And then for every 1 H plus, we know that we have 1 mole of K plus because it's a 1-to-1 ratio. The next thing we need to look at is this OH minus. The OH minus, when we reach this equivalence point, we're going to see a precipitate start to form of Fe+3 and OH minus. So at this point, the moles of OH minus is related to the moles of Fe+3, except we have 3 of those to 1 of those because our precipitate is ferric hydroxide. So a question you're probably asking yourself, or should be asking yourself, is if the OH is reacting here, the first thing it does is react with the H plus, and then it reacts with the OH minus in that order. Question is, why is it reacting with H plus first, and why, once all the H plus is gone, does it start to precipitate out for ferric hydroxide? You would think that could happen at the same time. It's actually a really cool situation. Ferric hydroxide is soluble in acidified solutions. So until all this H plus is reacted with the OH minus, we cannot precipitate out the ferric hydroxide that happens at that second equivalence point. So as far as the calcs go, when you're trying to figure out your moles of H plus, meaning moles of K plus, you're going to use volume 1. And there's a picture of this on the front of experiment 5. When you are trying to figure out your moles of OH minus, you're not going to use volume 2 because the precipitation actually is volume 2 minus the volume 1. Precipitation of the ferric hydroxide didn't occur until all that H plus was reacted. So make sure you use volume 2 minus volume 1 for this. If you have questions about that calculation, you can come and talk to me after the lab. So let's talk about how to start the lab. You're going to have a column provided to you and your partner. This is a one-shot deal. you're only allowed one column because these columns have to be prepared chemically for you before you can use them. They have to be what we call shocked. We got to make sure every single resin ball is actually covered with H+. The first thing you're going to do is you're going to open this up. It's just like a little burette clamp spindle, and a drop's going to come out. And I want you to use, it says in your procedure to use blue litmus. We're just going to go ahead and use pH paper. And I want you to check that this pH paper is not red. We do not want it to be acidic. On the pH paper bottle, there's a scale that shows you the pH colors from 1 to 14. You want to make sure that it is neutral, or it's more neutral, it's not acidic before you can start. Because remember, acidic means H pluses have escaped, and that will be fake H pluses indicating that there's potassium there when there's really not. So we want our column to be neutral. If it's not neutral, you're just going to continue to put water in here and let water just flow into some sort of vessel below over and over and over again until you get no color on that pH paper, until it comes off as being neutral. One thing I definitely want you to understand about these columns, you never, ever, ever, ever drop the liquid level below the resin. No dropping of the liquid level below. What does that mean? You can see up here, this is ridiculously high, but the water's up here. The resin bed is there. Never let the liquid drop into the resin. You're in control with this nozzle here, with that little turn tip. Do not let the water go into that resin. Once air bubbles get in there, that'll affect really how much stuff can go through. So no air in the column. All right, once you've verified that it's neutral, you are then going to go ahead and run your crystal through it. There is your known amount of green crystal dissolved. You're going to pour it into, and don't pour it all in one thing like they did here, the silly boys. You're going to pour it in here and run it through. Again, you're not going to drop this liquid level below there. So run it to about here, put in some water, run some more, and keep doing the water addition over and over and over again until you're assured that all of this green stuff has come through into the beaker on the bottom. You cannot run through with too much water. That is not possible. So keep running water through that column until you're 100% sure that all the green crystal, whatever's not stuck in the column from charge differences, is through. So you want to make sure all that K plus and all that H plus, excuse me, and all that Fe+3 is in the beaker below. All right. Oh, here is my picture. I knew I had the picture somewhere in here. This is the first equivalence point. This is the second. H plus starts to react with the OH first. Once all the H plus is utilized, we are no longer acidified, so we can start forming the precipitate here. And the precipitate is a bright, bright orange ferric hydroxide. Your setup, use a beaker, a stir rod. You're going to also need to use a pH sensor. The pH sensor cannot ding into the stir, okay? So this is going to be a tight squeeze because the burette tip also has to be on top. So spend a few minutes arranging this. This is a one-shot titration. If you mess this up, you have to come back in, personally reshock your column, run your sample through your column again, and then do the titration again. You're going to have to do all of this in one period. So hopefully you won't mess up. Run the stir as you're starting the titration. You probably won't have enough water in here to cover the pH sensor, so just doesn't matter. It doesn't matter how much water you add. Add enough water to cover your pH sensor and start stirring. You're going to start the titration, and you're going to start to see different colors. Watch the data on the screen of the LabQuest, and slowly you'll see the first endpoint happen. Then you'll see the second equivalence point come along, and you can see when you get to the second equivalence point, this is a bright orange color. It's like a longhorn. Go horns color. Here's a picture of the graph. You can clearly see, as indicated with the black arrows, your first equivalence point and your second equivalence point. So You can make note of this, but it's going to vary a lot. I've seen this happen anywhere between actually 7 to 12 mils. So you're just going to have to take this titration super slow, especially since it's a one-shot titration. And that second equivalence point, I've seen it happen anywhere between 15 and 30. There's no guarantee about this one. So again, take the titration super, super slowly. All right. If you need help with these calcs, just let me know. Experiment 6 is a 2-day experiment. You can set it up any day. You're going to basically drive water off of a sample. It's the easiest experiment of everything we're doing. I want you to find the mass of 2 evaporating dishes. Before you do that, and go ahead and turn to experiment 6 in your procedure if you haven't done so, I need you to label each with a number 1 and a number 2 and your initials. It's important for you to know the mass of the evaporating dish alone and the mass of the evaporating dish with the solid. And since you're doing 2 of them, you've got to label them 1 and 2 because it doesn't seem like it would be hard to confuse them, but it actually can get quite confusing. So once they're labeled, you're going to mass the evaporating dish, get that mass by itself, and then you're going to mass about 1 gram of solid. Do not, this is actually wrong. I do not want you to zero the balance. I want your mass to be the mass of the dish alone, just like it is in the data table of experiment 6, and then you need to get the mass of the dish plus your sample. It's not crucial that it's exactly 1.0. In actuality, what you can do is just take the remaining green crystal you have and split it in 2, unless you want to keep some crystal, which there's no reason to do that. Just split the rest of your sample in half, put 1/2 in one sample dish, the other half in the other evaporating dish. You're going to put them in the oven overnight. That oven will just be on for days, I guess, while different people do it at different times. And then you're going to place this in a desiccator that I'll have out. I'll show you guys how to use that in class when you're ready to cool your samples. But basically, it's a big glass container where with something called a desiccant at the bottom, where you can let this cool so water doesn't, because in Texas it's so humid too, where water doesn't jump back on and affect the weight. So we're going to let it cool in a dry place. Then you're going to weigh it again, and here's a picture of the difference between the hydrated and the not hydrated crystal. So basically, the mass difference will be the amount of water that you drove off, and you can easily determine from there the percent of water. I'm not even going to go over that because that's just super, super easy Chem 1 math. But that's it. Good luck with that. As soon as you are done and you have all your percents, this is an important issue I want you to pay attention to. The percents will fall sort of like this. They're not necessarily going to add up to 100%, but they might. You're now just going to do a big fancy empirical formula problem. You figured out your K and your Fe from your column chromatography. You figured out your oxalate from your titration in experiment 3, and you figure out your water from experiment 6. Once you know all those percents, you're going to pretend they're grams, assume grams. You don't even need to do this adjustment that he did. It'll be close enough to 100. Assume grams, convert to moles, divide by the smallest mole, and then find your coefficients, or your subscripts, I should say. This is the one thing I'm going to say, and it's the most important thing I'm going to say. You do not multiply by a factor to get a whole number. You're going to round all of your final moles to the nearest number, because one of your subscripts has to be a 1. One subscript is a 1. Do not round. Now, I don't want you to sit here and look at these answers and go, ooh, I know the answer. I know the answer to this puzzle because it's right in front of me. Remember, your grade is based on your data that's collected. I will put a series of pieces of information into a spreadsheet, and it's going to pop out what coefficients you guys should have gotten. They're not all going to be the same. So don't assume that this is the crystal answer you're going to get. You're just going to have to do your own calcs and find out. All right, that's it. See you in class.